Alright, we got another exercise here. Unfortunately, I'm going to confess there's some details in this proof that I don't fully understand, but they're very small details and they should be very quick fixes. For whatever reason, I'm just not. I think I really just don't quite understand induced representations, and this causes issues. But the facts, they aren't even very deep, but we'll get to them later on in this proof. So let's begin. So let's say that row 1 through row m are the irreducible representations of G. I want to prove that for all I from 1 to m, and just because I'm going to be using this a lot, I'm just going to call this capital I. So we want to prove that the dimension of all of these equals 1. I.e., if you look at these representations and you look at the underlying vector spaces, and the vector spaces have dimension 1. Okay. Since E is an abelian normal subgroup of G, we have for all I in I, and this is going to be a theorem from representation theory, it's just that the dimension of row I must divide the index of E in G, which is going to be just equal to the size of G. This is a product PQ. So, dimension of row I is going to be either 1 PQ or PQ. Let's see here. Let Ni just be shorthand. I probably could have done this earlier, but Ni is just the dimension of row I. We know that the order of G is equal to the sum from 1 to m of Ni squared. And so, let's see here. So if the dimension of row I happens to be equal to PQ, then the order of G, sum from J equals 1. Right, we're going to use J here because we're going to single out. So J equals 1 to m of Nj squared, which is going to be strictly greater than this particular Ni squared, but we know that this is PQ squared, which is strictly greater than PQ equals G. And so Ni is not equal to PQ. Why did I introduce Ni and then just write dimension of row I? Whatever. So this cannot happen. Likewise, if Ni equals, and this is for any I, obviously. So if Ni equals Q, so your Q is strictly greater than P. So if then we're going to have G is going to be equal to sum from 1 to m of Nj squared. And let's see here. This is going to be strictly greater than. Do we change anything in this computation? No, we don't. Ni squared. This is q squared, and q is greater than p, so this is going to be greater than pq, which is just the order of g. And so Ni is not equal to Q. Thus, for all I in I, we know that Ni is in, it's either going to be 1 or P. Now, to prove that it's not going to be P, so what we want is we want all of them to be 1. So we want each Ni to be equal to 1. So we got to prove that P cannot happen. And we have to do some really weird stuff in order to prove this. And it's actually going to involve, commutators, actually. So, and I actually, in another one of these exercises, I proved some facts about commutators that we're going to use. And whereas I proved them in that proof, because I was like, oh, well, let's say you don't know anything about these and you want to prove them, let's prove them. For here, I'm going to say, okay, refer to that proof if you want to prove these things. So, anyways, let n1 be the number of indices such that ni equals 1. So this is the number of irreducible representations of G of dimension 1, and NP similarly be the number of representations of G of dimension P, irreducible representations of dimension P. Then PQ is the sum from J equals 1 to M of Nj squared. What is this? So this is going to be, so Nj squared. So if we break up the sum of, part of this sum is going to be, we're summing over the indices that correspond with irreducible representations of dimension 1. And for each one of those, we're going to be summing up Nj squared, which is just 1 squared, which is just 1. And so that's going to give us, and there's Nj of those, capital N1 of those, so that's going to give us capital N1. All the other ones are going to correspond to irreducible representations of dimension P. And for every one of those, we're going to be adding up Nj squared, which is going to be P squared. And so this is NP times, well, here, let's write it as P squared NP, just so that subscript of P doesn't confuse at all. So let's see here, PQ is equal to this plus this. So thus, P must divide N1, because P obviously divides the left-hand side, so it must divide the right-hand side, so it must divide N1, because it certainly, it divides this P squared term. Okay, so next, note that multiplicative, the circle group, so multiplicative group of C, right? That's what we mean here. Yeah. This is an abelian group, because the actions are just multiplication by elements of the circle, and obviously, that's as nice as you can get in terms of group actions. And so it's commutative and everything. See here. So any homomorphism from, scroll down a little bit, any homomorphism from G to C cross or C times or whatever vectors through G mod G prime, where G prime is the derived subgroup of G or the commutator subgroup of G, whatever you want to call it. Let's see here. then every representation of G of dimension 1 is induced from a representation on G mod G prime. So this is the part where it's a little, I still don't quite see all the details here. I mean, it should be pretty obvious because we're not dealing with super complicated representations. These are, well, this is a representation of dimension 1, so it corresponds to something on the circle group. And so, here we naturally sort of have a map going from G to C cross, and this factors through G mod G prime. And so you could sort of make sense that you should sort of see, this should give you some sort of subgroup, or it should, yeah, this should somehow show you how to get a subgroup of G, that you could, and then you take, oh, this is a subgroup of G, and so it induces this. I don't really know all the details here, but I don't think it's a very difficult fact to prove if you know how to do this stuff. So every representation of G of dimension 1 is induced from a representation on G mod G prime, i.e. n1 is less than or equal to G, the order of G mod G prime. And that's because every element of G, every representation of G of dimension 1, that corresponds to the elements of n1. So that's going to give you a rep on G mod G prime. And so there's going to be a corresponding element of G mod G prime. And so there could be elements of G mod G prime which don't arise in this manner, and so all you conclude from this is that n1 is less than or equal to G mod G prime. So that's that. And since G mod G prime is abelian, every representation on G mod G prime will induce a representation on G. Okay, so I think there's more going on here involving induction that involves abelian groups that I just haven't quite fully digested. Okay, so every representation on G mod G prime will induce a representation on G. i.e. G mod G prime is less than or equal to n1. So n1 equals G mod G prime, and thus n1, let's see here, well, G mod G prime divides the order of G, right? Because it's just the order of G is equal to the order of G prime times the order of G mod G prime. So here, I'm going to write this on the next line. N1 divides the order of G, which is equal to PQ. So N1 is going to be 1, P, Q, or PQ. So we're back in this situation. But right away we know that P divides N1, so N1 is either going to be P or PQ. See here. So now we're going to assume for contradiction that N1 equals P. Then what? Do we also have this thing? Yeah, Q is not equivalent to 1 mod P. We still haven't used this fact yet. So here's where we have to use this. So we assume for contradiction that n1 equals P. Let's see here. Then PQ equals n1 plus p squared np. This implies that PQ is equal to, well, we plug it in, we get P plus p squared np. So we divide through by P, and then Q is equal to 1 plus P np. So then Q is equivalent to 1 mod P. Now obviously this contradicts that Q is not equivalent to 1 mod P. Thus, N1 equals PQ, and so NP equals 0. Right? Yeah, because that's we never ruled that out. Even though, so n1 equals this, and thus this divides this. So we knew that n1 had to be greater than or equal to 0, but np being equal to 0, that was never ruled out. So n1 is pq and np is 0. And so, hence, for all I in capital I, the dimension of row I is equal to 1. And that's exactly what we are trying to prove. And so this completes our proof.